Our last set of examples now have us modifying the area and trying to figure out what effect had originally occurred to the various linear dimensions. Or, another way to ask it, if I know how much I have to modify the area by, how will I also have to modify the linear dimensions of the object? So our first example talks about a circle of a circumference of 32 pi. So there is some known circle, and the circumference is given as 32 pi. It says that the area is going to be multiplied by a factor of 4. So I'm going to be looking at a circle of 4 times the area. So my area will be increased by a factor of 4. The question is, how would I have to modify the radius to achieve that? So what is my radius being modified by? One way to think about this. Originally we had a formula. That formula says that the modification of the area is equal to the modification of the radius squared. And I can use this as a tool to see how that radius had to change. If the area is modified by 4, that must have been whatever I did to the radius squared. If I take the square root of both sides, it means I must have doubled my radius. I increase the area by a factor of 4. I increase the radius by the square root of that value. I can also apply the same idea to non-circles. For example, maybe I have a square with a known perimeter of 36. The area is modified by a factor of a half. So I'm going to go down to half the area. The question is, what happens to the various side lengths as I shrink my area down? It's very tempting to say that I'm looking at half the area. But remember, if that were the case, if I were to shrink this dimension down by half, that's a quarter of the area, not half of it. Half this area is actually going to be a little bit larger of a space. So how do I get around this? Again, I apply this idea. Some factor, we'll call it f, squared had to yield a modification of 1/2. So let's solve for what that factor was. That factor must be the square root of 1/2, or 1 over the square root of 2. Now, there are various ways I can deal with this number from here on out. I could talk about modifying it by some factor related to that, or turn it into a decimal. I could take my calculator and simply say, calculator, 1 over the square root of 2, 1 divided by 2, hit the square root button, and I get a factor of 0.7. And that will also suffice as an answer. Again, I wanted to reduce the area by a factor of a half, so to accomplish that, my sides are being modified by a factor of 0.7, not a half. Remember, the area and the linear distances are going to be different. Let's look at one last example. Here I have a square, and the square has a known area of 49 square centimeters. I have the objective of quadrupling the area. So I want 4 times as much space. Now again, if I'm thinking brute force, that might mean drawing it all out. So there I've now drawn something that has 4 times the area. The question is, how have I modified the linear distances? How have I modified the dimensions of my original square? And again, I can work it out by using the numbers, or I could think about the rule. The factor by which I'm increasing the measurements squared will tell me how much the area is increased by. And I can work that backwards. Since I know the area was increased by a factor of 4, the dimensions must have been increased by a factor of 2. If I take the square root of both sides, I can get f by itself, and I see that that factor would have to be 2. And again, that matches with my original drawing. In order to get 4 times the area, each dimension had to be doubled. If I wanted to deal with 9 times the area, that would be tripling all of my measurements. 9 the square root of which is a factor of 3. One of the expectations is that without having to do all this brute force, you can use these rules to make predictions as necessary. I'll close with a final example. I have a known piece of perhaps patio, and I decide that I want to increase this patio by a factor of 5 in every direction. How much greater is my area going to be? Now, if I know how big the patio is to begin with, perhaps 2 by 10, it's a little slab on the back of the house, I could go ahead and actually calculate that out, calculate the increased dimensions, and continue work, and I'm still within the realm of math I could do on a cocktail napkin. But if I know the trick, I don't even need that cocktail napkin in order to solve the problem. Since I'm increasing all my dimensions by 5, the area is going to increase by a factor of 5 squared. And I'll be looking at an increased area of 25. I can then say, well, if I know that I'm looking at 30 square feet in the first place, 30 times 25 will tell me the area of my new patio. I don't actually need to work all these numbers out. But the rule that I need to remember is that if I increase all the dimensions of a two-dimensional object by a known factor, the area is going to increase by that factor squared. See you guys in class.